Okay, today we're going to begin a new chapter, chapter 10, Mechanicals and Sound Wave. At the beginnings of this chapter, we are going to see what is wave, and then we're going to see what is mechanical wave. After that, we're going to discuss sound wave as one of the examples of mechanical wave. So there are 5 subtopics in this chapter: 10.1 Properties of wave, 10.2 Superpositions of wave. So in these 2 subtopics, we're going to see the fundamentals of a mechanical wave, how they move, how they form standing wave, and so on. Okay, and then starting from 10.3, we are going to discuss about sound wave. So 10.3 sound intensity, 10.4 applications of standing wave, and 10.5 Doppler effect. Okay, so in 10.4, we're going to discuss a few musical instruments. We're going to see how they work and so on. 10.1 Properties of wave. In this subtopic, we're going to see what is a wave. Okay, and then we're going to learn how to distinguish between different types of wave, such as transverse wave and longitudinal wave. And at the end of this subtopic, we're going to see how to form an equation for a wave that is moving, which is for a progressive wave. What is wave? Wave is defined as the propagations of a disturbance that carries the energy and momentum away from the source of disturbance. So meaning that something is transferring energy while it is propagating. Then how about mechanical wave? Mechanical wave is defined as a disturbance that travels through particles of the medium to transfer the energy. Alright, now the difference between wave and mechanical wave is wave, it can be any wave. It can be EM wave, it can be mechanical wave, and so on. Okay, meaning that energy can be transferred with or without medium. But when it comes to mechanical wave, okay, it required a medium to transfer energy. Alright? So meaning that for mechanical wave, it cannot travel through the vacuum. Why? Because inside vacuum, there's no particle acting as the medium. But for mechanical wave, it needed a medium. So sound wave is an example of mechanical wave, and that is a wave that we're going to discuss in this chapter. So there are 3 types of wave in a mechanical wave. The first one is a transverse wave. Transverse wave, the particles is moving up and down, while the directions of wave is perpendicular to it. Okay, so it forms a 90-degree between the movement of particles and the movements of the wave. So directions of the wave, basically it represents the directions of the energy as well. Okay, if wave is going to the right, then energy is being transferred from the left to the right as well. So the second types of the wave would be longitudinal wave, where the particles movement is same direction as the particles of wave. It's not same direction, it's parallel to the directions of wave. So both of them, the angles between them is 0 because they are parallel to each other. Okay, whereas the last type, the types of the movement is a circle. Okay, this is what we call surface wave. It is combinations of transverse and longitudinal wave. Okay, so surface wave is not in our syllabus, but I'm just going to introduce it to you. I'm just going to explain it to you. What is a surface wave? So it is a combination of transverse and longitudinal wave. Okay, the particle were moving in a circles while the wave traveling, while the wave going from left to right. First example is transverse wave. Okay, so transverse wave is a wave that can be observed with our eyes. We can see it clearly. So for example, like in this diagram, you can see that the particle is moving up and down while the wave is traveling from the left to the right. It means that the energy is being carried from the left to the right. So one of the examples in our daily life would be musical instruments that come with strings. Okay, for example, a guitar. So when you pluck the strings, the wave actually is being generated, is being created along the strings. Okay, because you're transferring the energy from your fingers to the strings. Then the strings will start to oscillate, and because of the oscillations, it generates the sound. Second type of wave is the longitudinal wave. So a longitudinal wave is a wave that cannot be seen by our eyes, however we can hear it. Okay, we can listen to it. So for examples, now you have a source is generating a longitudinal wave, but you can't see it, you can't see what is going on, but you can hear the sound generated by it. Alright, so this is the movements of particles in a longitudinal wave. The wave is traveling from the left to the right. Okay, if you give it energy, it will just keep traveling. But if you look at these particles, this particle is just oscillating back and forth around its equilibrium positions. Okay, so it's just moving back and forth, but it's not a great distance. Okay, it's just a small distance from its equilibrium positions. So one of the examples in our daily life, okay, would be a speaker. So we can't see the sound being generated by it, but we can hear it. Okay, the reasons why we can hear the sound generated by the speakers is because energy is being transferred from the speakers. Okay, it's being transferred to the air molecule. So air molecule is oscillating to pass the energy from one molecule to the other molecule. Okay, that's why the wavefronts generated by these air molecules will carry the energy from the speakers to our ears. And when you notice, when you look at this particle, it's just oscillating around its equilibrium positions. Last one is a surface wave. Like I told you just now, surface wave is generated because of the combinations of transverse wave and longitudinal wave. So this is the movements of particles in a surface wave. When you combine the vertical oscillations and the horizontal oscillations together, okay, the particles will start to move on a circular path. While the directions of wave is still traveling from the left to the right, but these particles, it won't move forwards. It will just keep oscillating around the same equilibrium positions. So a typical examples in our daily life would be the water. Okay, now students always get confused. Students always thought that this is a transverse wave. Actually, that is not. Transverse wave is happening in the same medium. But if you look at this surface wave, okay, how we distinguish between surface wave and transverse wave is, surface wave is occurring between two different medium. First, for these examples, if you look at this diagram, above the wave is the air molecule. Okay, below the wave is a water molecule. So it is happening in between two different medium, two different materials, two different particles. Okay, and that is the main difference between transverse wave and surface wave. In a transverse wave, you have only one type of particles, whereas in a surface wave, you have two different particles. Okay, this wave is happening between two different medium. So before we look at the equations of a wave, there are a few terms that we must know in order to understand the equations, in order to generate the equations. So first one is something that you are very familiar with, which is the wavelength. The wavelength is a horizontal length of one cycle of the wave. Meaning that you are not going to look at the movement of particles. Okay, you're going to focus more on the wave itself, the distance between 2 points along the wave. Okay, so you can see here, the wavelength is also the horizontal distance between two successive crests, two successive truths, and any two successive equivalent points on the wave. What does it mean? Now let's look at this diagram. Two successive crests means from crest to crest. Okay, the tallest point, the highest point. Okay, the positive amplitude. So between two positive amplitude, this is the wavelength. Okay, two successive truth. What does it mean? It means two lowest point. Okay, these 2 points we call it truth. So it is a negative amplitude. So the distance between two negative amplitude, it is also equivalent to one wavelength. Or any two successive equivalent point. Okay, so from equilibrium to equilibrium. But don't get confused between this one and the other two. Okay, the one at the middles, the particle is directed towards different positions. It's moving towards different positions. Therefore, we cannot say this point is equivalent to the other two. Okay, if you look at the diagram, now let's call this one point A and point B, point C. Point A and point C, we say they are equivalent. Why? Because the particle, both of them, they are moving down. Okay, so they are moving towards same directions and they have the same shapes. They are looking at the same position. So we say they are equivalent. But when it comes to point B is not equivalent to point A and C, even though it is located at the origin, at the equilibrium positions. Why? Because at point B, your object is moving upwards. Your particle is moving upwards. Okay, so because of the direction, we say point B is not an equivalent point to A and C. Okay, next is the wave number. Wave number is something new to you. Previously, we have seen what is frequency, right? So frequency, it tells us how many complete cycles in 1 second. Same goes to the wave number. Okay, it's going to tell you how many cycles, but not in terms of time, but it is in terms of unit. So it tells you how many cycles is being generated in 1 unit of distance. Right, so such as a 1 cm got how many cycles, 1 meters got how many cycles. So let's look at this example. Now, according to this diagram, it tells you the wave travels by 2 cm. Okay, the length of the wave is 2 cm, and then 4 cycles are being generated in this 2 cm. Okay, meaning that the lambda is equals to 0.5 cm, because lambda is the wavelength of 1 cycle, is the distance traveled between the 2 successive points. Then how are we going to calculate wave numbers? Now you have 4 cycles in 2 cm. But when it comes to a wave number, we want to see per unit distance. Okay, if you are given cm means per cm. So 4 cycles in 2 cm, what I'm going to do, you just divide them. Okay, so k is equals to 4 cycles divided by 2 cm. Therefore, the wave number is 2 cycles per cm. Well, in a calculations, you don't have to show the cycle. You just have to write down the unit as cm-1. Okay, so the general equations for wave number is 2 pi over lambda. Why? Because 2 pi, it represents 1 complete cycle. Okay, so you want to see how many cycles in terms of a cm. Okay, in terms of a meter divided by the lambda, which is the wavelength. Okay, so this is 1 cycle, 2 pi, and then this is a 1 wavelength. So when you divide it, you're going to find out how many cycles is being produced in 1 cm. So the SI unit can be a radians per meter, radian per cm. SI unit is in meter, but the other unit that can be used is a radian per cm, radian per mm, or you can just write out as a per meter, per cm, per mm, and so on. Now, just now we look at the wave motions, right? We say inside along the wave, the particle is just moving up and down. It doesn't travel together with the wave. Meaning that when it comes to a wave motions, okay, every motion, it consists of a x displacement and a y displacement. Where x displacement is the motions of the wave and the y displacement is the motions of the particles. Okay, so x displacement, we also call it wave displacement. It is the distance of the particles from the source of the disturbance. So for examples, now this is the source of a disturbance. Okay, so let's say you drop a stone here, and then the water is start to propagate. Okay, so this is means that it is from the source of disturbance. You're going to look at the distance traveled by this wave. Okay, the distance traveled by the energy. So this is your x displacement. Then the y displacement is what we call particle displacement. Okay, it is the displacement of the particle from its equilibrium positions. All right. So based on the diagram above, okay, this is the source of disturbance. So the energy, the wave is traveling to the right like this, all right? So every point along this wave actually consists of one particles. And this particle is just moving up and down. And this is what we call y displacement, okay? Every particle is just moving up and down. It's unlike the wave traveling from one point to the other point. The particles can only oscillating around its equilibrium positions. So when you combine, this is actually what are you going to see, okay? So the wave is traveling from the left to the right. Let's assume this y exists as a source of disturbance. So the particles is oscillating up and down, and then the wave is traveling to the right, meaning that the energy is being transferred from the left to the right, if according to this diagram. So this slide is just going to show you what is the difference between transverse wave and longitudinal wave, and how particles and wave move in a transverse wave and longitudinal wave. Alright, so the first one is a transverse wave. So as you can see here, the wave is moving from the left to the right, and this particle is just moving along this line. Okay, even though the wave is keep propagating, but this particle is just moving up and down. For transverse wave, it is not hard to imagine. Okay, the thing is just how it moves in a longitudinal wave. So this is the longitudinal wave. As you can see here, the wave is traveling from the left to the right, okay, based on these arrows. And you look at what happens to the particles. The particle is just oscillating around its equilibrium positions. Just a very, very short distance only when you compare to the distance traveled by the wave. Alright, so make sure you are clear what is the difference between the wave displacement and also the particle displacement. Next, we are going to see equations of progressive wave. Now that we have seen what is wavelength, what is wave number, and also what is the x displacement and y displacement, we have enough information to form an equations of progressive wave. But before that, what is progressive wave? There are conditions if you want to apply these equations. So a wave which travels continuously in a medium in the same direction without a change in its amplitude is called a progressive wave. Based on this statement, you know that amplitude is constant. Why? Because in order to call it a progressive wave, it tells you that amplitude cannot be changed. The amplitude must be the same throughout the motion. Alright, so the general equations for the wave traveling to the right, we are going to write it down as y equals to a sine omega t minus kx. Is it important to know the directions of motions? Yes. Why? Because the sign conventions here, it represents the directions of the wave. If your wave is traveling to the right, then we use a negative sign to represent it, okay, in our equations. But if your wave is traveling to the left, or we say in negative x direction, then what should we do? We replace the negative sign with the positive sign. So basically the plus minus sign in between omega t and kx, it tells you the directions of the wave. Alright, then if you look at these equations, okay, if you look at these equations, the things that we know that must be constant is the a, right? And then in previous chapter, we also know that for a wave, okay, we always take the omega as a fixed value as long as it's traveling in the same medium, meaning that k would also be the same. So in this one equations, we have three constant value, which is a, omega, and k. Okay, meaning that if you want to form an equations, these three values are the values that you have to substitute into the equations. Alright? So this is how the wave moves, okay, the moments of the wave. So the wave traveling from the left to the right, we have a positive sign. And, from the left to the right, we have a negative sign. And then wave traveling from the right to the left, we have a positive sign. From right to left, positive. From left to right, negative. Since we have wave displacements and also particle displacement, meaning that we're going to have two different velocity as well, wave velocity and also particle velocity. So first we're going to see what is a wave propagation's velocity. Okay, wave propagation's velocity, since it's about wave, obviously we're going to use it for the wave motions along the x component. So the distance traveled by wave profile per unit time, that is what we call wave propagation's velocity. Okay, so you see, you look at this diagram, the wave is traveling from left to the right. You're going to look at what happens to this whole wave. You're not going to just look at one point. Okay, so figure shows a progressive wave profile moving to the right. So it moves a distance of lambda in times t. All right, so this one cycles. Okay, it moves it in amounts of time t. Therefore, we have a v equals to lambda over capital letter T. Then how are we going to expand these equations furthermore? So other than v equals to lambda over T, since we know that t is equals to 1 over f. Therefore, we can rewrite the equations as v equals to f lambda. So this is the general equations that we use for our wave motions, okay, for the wave propagations velocity. So you have two equations, remember? You have a v equals to lambda over t, and because t is equals to 1 over f, so you can rewrite it as v equals to f lambda. Most of the time we use these equations, but sometimes this one might be helpful as well. Next, we have particle vibrational velocity. Okay, so in the previous slide, we have seen what happens to wave motions. Now we're going to see what is the velocity of a particle that oscillates up and down. So the definitions of particle vibrational velocity, it is the speed of a particle vibrating with simple harmonic motion around its equilibrium positions. So let's take a look at this diagram. So you have a wave like this, and then the particles along the wave, it is oscillating up and down to generate this wave, right? So meaning that the displacement, okay, the y displacement, which is the particle displacement, it changes with time. As time passes by, the positions, the height, the displacement traveled by this particle is different. Okay, meaning that if you want to calculate the velocity, okay, you have to differentiate its equations. It's a displacement. Why? Because displacement depends on time, changes with time. Therefore, the velocity also changes with time. So Vy equals to dy over dt. So previously we have seen what is the equations for y. We have y equals to a sine omega t plus minus kx. So you just substitute these equations, okay, into a dy over dt. Therefore, you're going to get d over dt bracket a sine omega t plus minus kx. Try to recall what have you learned in chapter 9. If you differentiate the sine, what are you going to get? You're going to get a cos. So you have a Vy equals to a omega cos omega t plus minus kx. So it is very similar to a chapter 9, the way you calculate its velocity. Alright, the only difference is for this chapter, it comes with a plus minus kx. So this is very important. Keep in your mind that the wave velocity and the Vy is not the same. This V, it is the V for the wave profile, okay, for the wave along the x component. Whereas this V is a V for the particles, okay, it's a V for the particles, and this is only for the y components. So in short, the difference between them is first in terms of the equations. For wave propagation's velocity, we have V equals to f lambda. For particle vibrational velocity, you have to differentiate its displacement. And then when it comes to value, for the wave propagation, it is always constant. And for particle, like I told you, it changes with time as the wave passes by. Alright, because your y also depends on time, therefore v also depends on time. Then for accelerations, for wave propagation, since the v is constant, therefore we have 0 accelerations. And for particles, you just have to differentiate your velocity, like what we have been doing in chapter 9. So in this chapter, we are going to look at two different graphs. The first one is y against t graph, and the second is a y against x graph. So why two graph? Because based on the general equations, we have y equals to a sine omega t plus minus kx. According to these equations, you have three unknowns, which is a y, t, and x. Okay, meaning that you can use a graph to show the relationship between y and t, and also the relationship between y and x. Now let's start from a displacement time graph. What is a displacement time graph? It shows you the displacements of the particles in the wave at any particular instance from the origin. Okay, or it shows you how displacement varies with time for one particles in the wave. So meaning that if you want to look at the relationship between y and t, then the distance should be given, because it says at any particular distance, right, from the origin. So meaning that x is given if you want to sketch a y against t graph. Alright, so if you sketch a y against t graph, this is what you're going to get. This is just a general shape, of course, okay? You can have a cost function as well, okay? But this one, I'm just going to show you based on the sine function. So from the YT graph, the information that we can get is the amplitude and also the period, okay? X is given, remember, in the YT graph, X is given, and then after you sketch the graph, the information that you can get from the graph or the information needed to plot the graph is the amplitude and period. And then the next one is the displacement distance graph. So what is a displacement distance graph? It shows you the displacement of particles in a wave at any particular time. Okay, at a particular times means t is given now. Okay, t is given, then you sketch a graph to see the relationship between y and x. So after you sketch the graph, what are you going to get? You're going to get y against x. Now not y against t anymore, because you're sketching the displacement distance graph. So meaning that now if you have one complete cycle, the information that you are going to get is no longer period. The information that you're going to get is the wavelength, lambda. Alright, so from the graph, we can either obtain amplitude or wavelength, or you are going to need these two pieces of information in order to sketch the graph. Okay, so it is exactly same as your chapter 9. Either you extract the information from the graph, or either you will calculate all of the informations and then you transfer it, you put all of those informations into the graph. Okay, you form a graph based on the information given. So it is very similar. The only difference is now the equations is slightly more complicated. Okay, because it has a plus minus kx there. So remember, if you want to sketch displacement time graph, then x will be given. If you want to sketch a displacement distance graph, then time t will be given.